reference is the frame of reference of the aircraft, XYZ. The second frame of reference is that identified by the aerodynamic forces, lift, side force, and drag, that act on the aircraft. These two frame of reference are not necessarily aligned with each other. So we need to transform one frame of reference onto the other. So we saw that there are two rotations that we perform to shift the aerodynamic forces onto the body frame of reference. The first rotation is, if this is X, this is Y, and Z is going inside the board. The first rotation we perform is by this angle here, which is the side lift angle beta. So this takes us onto an intermediate frame of reference, Y prime, X prime, and Z stays the same. So the rotation of the angle beta is around the Z axis. This is the first rotation. Then we have a second rotation, which is Z plane. So here is X prime. This is Z, which hasn't changed. And then we have the axis Y coming out of the board. So the second rotation is alpha, the angle of attack, so rotation around the line. Okay. This brings us to the final frame of reference, X, Z, and Y. Vertical down. And Y comes out of the board. So with these two rotations, we have now shifted the frame of reference so that the aerodynamic forces, lift, drag, and side force, can be expressed in terms of the aircraft frame of reference XYZ. So we come up with this system of equations along the X, Y, and Z direction of the aircraft. Okay, so we can see that the forces act along different axes. The lift doesn't act only along the vertical axis then. It also has contributions around the x-axis. And so for the other two forces, drag doesn't only act in the x-axis. Okay. It also has contributions in the vertical and y direction. So, once we have derived this system of equation, we introduce some simplifying assumptions. The simplifying assumptions, the most important one of which are that we are going to ignore higher order terms, and we have small angles, so alpha, the angle of attack, and beta, the side slip angle, are very small. So we can, when we're looking at the trigonometric functions here in the system of equation, the cosine of the angle becomes 1, well, the sine of the angle becomes the angle as well. So we get rid of the errors or the trigonometric functions in that system of equations. So now that we have a let's say simpler system of equations, those are the forces that are acting on the aircraft. So the next step is to calculate the moments that are generated by the forces acting on the aircraft. The moment, or the moments, the moment vector is given by the product of position vector I, that is the difference between the center of mass, where the force is applied and the center of mass, multiplied by the force. So we have M equals R vector F. So this is the most generic expression. With this, you can calculate and you can look at the effects that a perturbation has on the aircraft along any axis, yaw, pitch, and roll. Okay, so yaw you look at L, pitch you look at M, and yaw you look at N. So we are going to look at the specific case of a pitching moment. So we want to look at the moment component M. So we have simplified the forces by getting rid of the trigonometric terms, and we make the assumption that the aircraft is not subject to side force, so we can get rid of side force in the equation. So we then apply the R vector F equation, and we come up with this. Now the aerodynamic forces, lift, drag, and side force, can all be expressed using a generic formulation, which is 1/2 rho v square surface times coefficient. Okay? So we substitute that specific equation, so having CD for drag and having CL, the lift coefficient for lift, into the equation. And then we have, in this particular case, another simplifying assumption, the assumption being that the drag coefficient is constant. So the drag coefficient does not vary as a function of the angle of attack. This is not the case for the lift coefficient, for which we introduce that linear equation CL0 plus A alpha. So we substitute this into the equation for the moment, and we see that in this equation here, there are some terms that we can get rid of, and these are the higher order terms. So the last term in the equation, which has an alpha squared term, that is a second order term because we have made the assumption that alpha is small. Okay? And then we have another term, which is the term Z minus ZCN, which multiplies 1/2 rho v square SCL alpha. That is another second order term, because we saw yesterday that the distance between the center of mass and where the force is applied in the vertical direction can be assumed to be very small. Hence we have one small term, ZF minus ZCN, which is multiplied by another small term, alpha. So this gives us a second order term, so we can get rid of that. So the equation that we are left with is this one. Okay, so now we have to understand that the aircraft is pitching, so it is moving in this direction. So this means that if we have a force, let's say on the tail plane, or in the tail wing here, a lift force here, and the aircraft is moving in this direction, so this is the center of mass. Okay. What happens to the velocity of this element here? So the aircraft is moving with velocity v in this direction. Okay. But what else do we have to consider? That the aircraft is pitching. So we have a component of angular velocity due to the fact that the aircraft is moving up and down. So this point here, in fact, any point on the aircraft that isn't the center of mass will have a linear velocity and then a contribution to the velocity due to the pitching motion. Is this clear? Why not? What isn't clear? Sorry? What you don't understand? Okay, so this aircraft is moving in this direction. Okay, so at the moment, all the points on the aircraft are moving with the same velocity. Okay, now if the aircraft isn't moving like this anymore, but starts pitching, so rotating around around the y-axis, okay, you will see that there is a additional velocity component due to the fact that there is this motion, this angular motion. Okay, so not only is this point moving with velocity v, but it is also moving upwards. Okay, after 1 second, the aircraft will be like this. Okay, so it is pitched down. Sorry. center of mass hasn't moved. Okay, it is still, the center of mass still moves with velocity v. But this point here on the tail plane, the tail wing, has changed. Okay, so there is an additional element to the velocity vector of this point here, which isn't just the linear velocity v, but it is a contribution given by this distance here, r, and q, the angular motion. Okay, so this point here is not moving only in this direction. It is also moving upwards. Okay, so you have the velocity from this motion, and then the velocity from this motion. Okay, so that is why you have two contributions to the velocity of any point away from the center of mass. Is it clear? Yes? This is important, so if it's not clear, I'll try to explain it again. Are you sure? Don't be shy. Yes? Here. Here. Okay, the angular velocity will be the same, q. That doesn't change. What changes is the magnitude of the component, of the additional component to the velocity due to the angular velocity. So, the velocity is given by, the total velocity is given by the linear velocity, which is this one here, plus, let's call it the angular velocity component. Okay, this term here is given by omega vector r. Okay, so omega is constant for any point on the aircraft. It's always q. But r is different. Okay, r is the difference from the center of mass to the point that we are considering. So this r here, if we are considering this point, okay, will be different from this one here. Okay, so this r is going to be greater than this one. So the angular velocity contribution will be greater at this point than at this point. Okay? Any other questions? No? Are you sure? Okay.
Yeah, I think consider in the same direction as the linear velocity.
Okay, so we go back to Coriolis theorem. That is that the absolute velocity, let's call this the absolute velocity, let's call it df, okay, is given by the velocity in the body frame of reference plus the angular contribution omega vector r. Okay, so in the more general terms, the vector df will be uf df the components of the angular velocity omega. And then r will be given by x minus xf, y minus yf, and z minus zf, where the subscript f indicates where the force is being applied on, is acting on the aircraft, the wing, the fuselage, the tail, the tail wings, and so on. Okay? Yes. Sorry? This one here. Oh, here. Yes, sorry. So this is the distance between the center of mass and where the force is acting. Okay, so let's keep this in mind. And we go back to this equation here, okay? Now, what is the definition, the mathematical definition of the angle of attack? What is it determined by? It's determined by the ratio between the vertical component of the velocity divided by the overall vector velocity with tangent. Okay? Since we have made the assumption of small angles, this becomes alpha equals W over G. Okay. Okay, is this clear? Yes? Okay. So we see that we have the component of the linear velocity, W. So let's go back to our V equals V plus omega vector R. Okay. That in our specific case, we're looking at the pitch moment. Okay, so the component of the angular velocity will be 0 0 Q and 0. Okay. So if we develop the scalar, if we develop this product, okay, with omega being 0 Q0, we will find that okay. So, what can we do? First of all, we substitute this equation for alpha f into here. So we have Wf over Ef and here. Okay. And then we substitute this equation for Wf into here and here. So what do we have? This is x. So omega Wf is equal to W plus Q x minus xn. Sorry. Okay, so now the next step is to look at these two terms, this one here and this one here, which we can break down, we can separate the terms and write them as W divided by Vf minus Qx minus Xn Vf. And the same we can do for this. Okay, so what does this term here W over the F represent? It represents the angle of attack of the aircraft, not of the surface that we are considering. Okay? So this and this you can write as alpha. Okay? So the alpha is the angle of attack that the aircraft has, not that the surface that we are considering has. Okay, that was alpha F. The term here and here. Okay. Everybody following? Yes. This one here. What did I write earlier? Oh, the other way around. This one. Okay. Anything else? Okay, so the last step is to get rid of the 1/2 rho b square coefficient surface by normalizing. So we divide all the terms that appear in the equation by that term there, which is wing. Okay. So if we divide all the terms in this equation by 1/2 rho df squared s times c, we will have is, what is this surface area here, S, that appeared in the equation and that is still here? This surface S is the surface area of the component of the aircraft that we are considering, where the force is acting. So this can be fuselage, wing, tailplane, tail wings, and so on. Anything. It depends on where the force is acting. Okay. So now we can see that we have some common terms, or rather terms in which similar quantities appear, namely alpha here and q, the pitch moment, the pitch velocity. Okay. So what we can do is collect all the terms that have common elements. So we can collect this and this. Okay? It's a term multiplied by alpha, another term multiplied by alpha. We can collect this, the terms multiplied by Q, okay? And then we will also have terms in which neither alpha or Q appear, this one and this one, okay? So if we do this, what we can have is we can have that the pitching coefficient, which is the moment divided by our 1/2 rho d square rho d square S wing C bar. Okay. The moment coefficient, the total moment coefficient will be given by the sum of Cm0, then Cm alpha multiplied by alpha, so the pitching coefficient, plus a term CMQ multiplied by Q. Okay, so what I have done here is simply collected all the terms that appear in this equation that either have alpha, Q, or neither. If they have alpha, they will appear in Cm alpha. If they have the angular velocity Q, they will appear in CMQ. If they don't have either, they will be CM0. Okay. Is it clear? Okay. So we have this equation here. Okay. So what I can do is develop the whole product. So I will have M divided by 1/2 rho d square S wing C bar, okay, which is equal to, we have this term minus X, minus XCM, okay, which multiplies this term here, okay, let's call it multiplied by alpha, okay, but this term here also multiplies this, so we have plus which multiplies this, so Q X minus XCM dF, okay. Yes? Then I have this term here, minus S DL0 S wing C bar. Okay, that stays the same. Then I have this term here, minus S wing C bar A alpha. And this term here, minus SWCA also multiplies this. So plus Q XZ minus XCM dF. Okay? And then we have this last term. that we have this equation, you can see that there are some terms which are multiplied by alpha. Some terms that are multiplied by Q. Okay, and other terms that don't have either Q or alpha. Okay, so these ones will go here. These ones will go here. And here. Okay, is it clear now? So, we can collect the terms so that we have for CM0, we will have the common term, surface divided by surface of the wing chord, multiplied by xf minus xcm, CLO, minus red f minus xcm, CD. Okay. Then we have CM alpha. And then we have CMQ. Okay, so what do these terms mean? What is their significance towards the stability of the aircraft?